Namaste, dear viewers. I am Dr. Sunita Goyal, working as an associate professor in the Department of Applied Sciences and Humanities at ABES Engineering College. Today, we'll discuss about NMR spectroscopy. It will be part 2. In the first part, we have discussed about the theoretical concept of NMR spectroscopy, and now in part 2, we will deal with the different type of informations which we can gather from this spectroscopy, from this technique. Yes. So in the NMR spectroscopy, there are different types of applications, or we can gather information for the structure of a compound, of a molecule. Now, we take the example of position of signals. What type of positions of signals will there be on the NMR spectrum will be decided by the set of protons which are equivalent and non-equivalent. So, a set of protons with identical environment absorbs the radio frequency energy at the same field strength, and they are called as equivalent because they give only one PMR signal. PMR signal means proton magnetic resonance signal. So, when a set of proton which belong to the same chemical environment, they will absorb the radio frequency region at the same field strength. They will absorb this energy at the same field strength. Therefore, we will call them as equivalent protons, and they will give only one type of NMR signal. While if the protons, they belong to different environments, they belong to different chemical environments, therefore they will be magnetically different. So they are known as non-equivalent protons, and they will give rise to different PMR signals on the NMR spectrum because they are non-equivalent protons. So here there are so many examples are there in which we can identify the number of signals, we can calculate the number of signals. For example, here in this example, we can say that there are two sets of protons, 1 and 2, but both are chemically same, magnetically same. They will absorb radio frequency at the same field strength because they are at the equal distance from oxygen. We can see in the next slide also, there are total six protons in the set of 2 methyl groups, but we can see first methyl group as the 3 protons containing, and it will be giving a signal. And here in the second set of CH3 or the methyl group, it is again 3 protons are there. It's a set of 3 protons, so there will be again a type of signal or the similar signals. So number of NMR signals in this molecule will be 1 only. In the second molecule, there are 2 sets of protons. In set 1, there are methyl groups, and in set 2, there are 2 hydrogens of methylene. They are in the different chemical environment as we see their distance from chloride, which is an electronegative atom. So A type of signals for 2 hydrogen atoms of methylene, and B type of signal for due to 3 hydrogens of methyl groups. So there are 2 types of sets, or 3 protons are equivalent, but they are non-equivalent to 2 protons of methylene, and 2 protons are equivalent, but they are non-equivalent for this methyl group. So in this molecule, we will be having 2 NMR signals. In the third molecule, third example, we can see here there are 3 sets of protons, 2 types of methyl protons on the terminal positions, and in the vicinity of oxygen, there is 1 methylene proton set of 2 hydrogens. So we can see 3 types of protons are present. So there will be 3 NMR signals. In this molecule, there is the same CH2Cl and it is also CH2Cl. That means the chloride environment is in the vicinity of both the carbons, both the protons. Therefore, all the 4 protons will be similar to each other. So, there are only one type of signal of 4 protons. So, NMR signal is only one. In the next molecule, we can see here, there are uh, two halogen atoms, but they both are different. Their electronegativity will be different. That will affect the protons of the vicinity of these methyl groups, terminal methyl groups. So, if both the methyl groups are same as in the last case, then this methylene and this methylene will be same. But here the chloride is different than bromide. Therefore, there will be one NMR signal, one more and one more. That means 3 different signals will be there because 3 types of protons are present. So here CAB and C, that means 3 signals will be there. Now, when double bonds are there, double bonds are there and protons are attached on these carbon-carbon double bonds, then how can we say they have the example of 1,1-dichloroethylene? There are two chlorines on one carbon atom, and cis to them are 2 hydrogens. This proton is cis to chlorine, and this is again cis to this chlorine. Therefore, they both will give the same signal. Here, in this example of 1-bromo, 1-chloroethylene, there are 2 protons, but 2 different halogen atoms are there, which are cis to them. So this proton is cis to chloride and this cis to bromide. Therefore, it will be A type of proton and it will be B type of proton. So 2 NMR signals will be there in the NMR spectrum. In this molecule, the third one, chloroethylene, there are 3 NMR, there are 3 protons, one H, this H and this H. This H is on the same position, carbon at which chlorine is there, and this is cis to this proton. Then this HC, this is cis to this, and it is on the transposition of chloride. And here, this is third type of proton, which is cis to chloride. So there are 3 different types of proton. It will be having 3 different types of signals. So we can say in the first molecule, we are having one type of NMR signal because one type of hydrogen is present. Here in this molecule, we are having 2 NMR signals as 2 types of hydrogens are present. And in the third molecule, 3 NMR signals will appear as 3 types of hydrogens are present. Now, the next topic is shielding and de-shielding of protons or shielding and de-shielding effects. When a molecule is placed in a magnetic field, its electrons are made to circulate. As we all know that the protons are attached with the carbon or other molecules with the help of bonds, chemical bonds, and these chemical bonds contain electrons. So these electrons are also charged bodies and they get circulated. They remain circulated and therefore they generate some electric field, and there is some magnetic component of that magnetic field which is known as a secondary magnetic field or induced magnetic field. This magnetic field is due to the circulation of electrons in the chemical bonds, which may either reinforce this magnetic field. The direction of this magnetic field may reinforce, means align with the field, or it may oppose the field. Which field? Applied magnetic field. So when the molecule is kept in an external magnetic field, this induced magnetic field can reinforce or oppose that external magnetic field. We can understand this here by 2 situations. Here, we are taking the example of shielded proton, and here we are taking the example of de-shielded proton. In case, suppose this is the direction of the external magnetic field which we are applying to the molecule through the instrumentation of NMR. So this is applied field from the strong magnet or from the external magnet. And here also this is the same case. But in this, in case of shielded proton, what happens that the induced field is in the opposite direction. What is this induced field? This induced field is the field which is generated inside the molecule in the through the electrons in the bonds. So its direction is in the opposite way. So induced field opposes the applied magnetic field. While when it is a de-shielded proton, then there is the induced field in the same direction as the applied magnetic field. So resultant field will be what? It is shown by the green arrow. Here in the case of shielded proton, it is the subtracted one. This much is the external magnetic field and this is the opposed field. Therefore, the resultant, what a proton fields experiences is only this one. So this much is the field which a proton experiences. And in the another case, this is the this is the resultant field which a proton experiences. That means the applied magnetic field is this much. But as the induced field which is created in the vicinity of the electrons, in the vicinity of the protons due to electrons, circulating electrons, as it is in the same direction of the external magnetic field, the resultant magnetic field at the proton will be enhanced than the external magnetic field. Therefore, the effective field experienced by proton is this much and effective field experienced by proton is this much. So this type of proton we are saying shielded proton, and it requires a stronger magnetic field. Therefore, this type of signal will appear in the NMR spectrum at the up field or the high field. Or we can say this type of signal or peak to up field or higher field. While in case of shielded proton, it requires a lower magnetic field. It requires a lower magnetic field because the field is reinforcing, the induced field is reinforcing, therefore it requires the lower magnetic field. Therefore, this signal will be on the downfield side, or this type of peak is known as downfield peak. Now, as we have understood in the last slides, we can see here that the shielding of proton in case of induced field, in case the induced field opposes the applied field, the field felt by the proton is diminished. Such a proton is said to be shielded. While this shielded proton requires a strong magnetic field, and for what? To produce an absorption signal, and thus it is said to be upfield peak. And the de-shielding of proton, what's that? If the induced field reinforces the applied field, the field felt by the proton is increased. Such a proton is said to be de-shielded. A de-shielded proton requires a lower applied field to produce an absorption signal, and thus it is said to be a downfield peak. So, by knowing the shielding or de-shielding of these protons, we can see the position of these signals in the form of chemical shifts on the NMR spectrum. The positions of the signals in an NMR spectrum are based on how far they are from the signal of the reference compound. Now, what is this reference compound? Reference compound is tetramethylsilane, TMS. This is the structure of tetramethylsilane. Here in the center, it is a silicon atom. And with the silicon atom, the 4 valencies of silicon are saturated by 4 methyl groups. And these 4 methyl groups contain total 12 hydrogens. And all these 12 hydrogens are equivalent to each other. Therefore, they will give only one signal. Moreover, the silicon atom is more electropositive as compared to carbon. Therefore, it releases electrons towards carbon, towards these methyl groups. Therefore, these protons, all the 12 protons are shielded protons or very well shielded protons because the electron density is towards the methyl groups. So, why we use TMS as a reference? Because it has 12 equivalent protons, therefore they will give only a single peak, and that peak due to the 12 hydrogen atoms will be very intense, and all the 12 protons are having the same chemical environment, and they will resonate or they will flip magnetically at the same field strength. So they will give a only a single peak. And their protons are highly shielded because of the electropositive nature of silicon as compared to carbon. So the NMR peak of TMS will be on the rightmost or at the right extreme of the spectrum than most other peaks. So most of the other peaks will be on the left-hand side from the TMS. Then it is non-toxic and chemically inert, therefore it will not react with our sample and we can retain our sample very well. Moreover, it is its boiling point is very low, therefore it can be volatilized very easily and our sample can be retained. Here we can see in this spectrum that how we see different signals and how we can know about the chemical shift. So this is the spectrum, and in this spectrum, the signals start appearing from 0. Yeah, this is known as, this chemical shift is denoted by delta in ppm, that means part per million. So the scale starts from right hand side to left hand side. Yes, this way. This is the signal of TMS is kept at 0. Therefore, it is known as reference. To reference, we keep at the 0 position. And we can see here it is a long peak of TMS and it is a single peak. And it is at the rightmost position. And any of the signal can be seen, most of the signals can be seen left-hand side than this TMS signal. Here we can see there is a molecule which is containing 6 protons, and these 6 protons are in the 2 sets. This is one set of 3 protons methyl group. This is another set of 3 protons methyl groups. So these 3 groups, the 3 protons are different than these 3 protons because in the center it is an ester group, COO. This carbon and these protons are more closer than towards this due to this oxygen, and these protons are comparatively shielded than this oxygen. Therefore, these are the shielded protons, while these are the de-shielded protons. So in this set, 3 protons, these are de-shielded and these are shielded. Here in how can we see in this chart paper or in this spectrum, we can see that the shielded protons will be on the right hand side, or they will be nearby to the TMS. So these are the shielded protons, because we are saying that TMS is highly shielded, then shielding will be lesser and it is converted to de-shielding from right to left side. So this side is the de-shielded side and this side is the shielding side. So shielded signals will be on the right hand side and de-shielded will be towards the left hand side. So de-shielded is HB. HB protons are more de-shielded, therefore they are on the left hand side, more left hand side there where the delta value is high. This is something 3.7 approximately. And HA protons are shielded, they are more towards TMS, its delta value is 2. So the de-shielded protons will have high delta value, delta value, while the shielded protons will have low delta value. We can see it here. We can understand it more here. The shifts in the position of NMR signal arising from shielding or de-shielding by electrons are referred as chemical shift. It's a measure of how far the signal is produced from the proton from the reference signal, that is the TMS signal, and is usually measured using delta scale. So the formula of chemical shift delta will be equal to frequency of the signal minus frequency of the reference upon spectrometer frequency. This is the frequency at which our spectrometer operates. Multiply by 10 to the power 6 because we are taking delta or the chemical shift in part per million. So it is the unit of chemical shift or the delta value. And this the proton chemical shifts range from 0 to 10 almost for all the protons. However, it may not be the case for all always. And the position of signals depend on the chemical shift. So in the last slides, we have seen here, this is the chemical shift value. Here, this is the chemical shift value for HP protons. So as the value of delta, that is the chemical shift. Yeah. So in last slide also, we have discussed that this left-hand side region is the de-shielded region for the protons and right-hand side is for the shielded protons. And TMS at the most shielded region for which delta value is equal to 0. Now the splitting of proton signals. These signals, as we have seen in the last spectrum, there were only 1 peaks, but this is not the case actually for the high resolution spectrophotometers. We will see there splitting of these signals or multiplicity of these signals. So splitting or multiplicity of a signal arises due to the presence of non-equivalent neighboring protons. The splitting pattern of a given molecule, given nucleus or set of equivalent nuclei can be predicted by a rule, that is n plus 1 rule. What is n here? N is the number of protons which are present on the adjacent carbon. So how we can apply it? We'll see here. If a proton has no neighbors, then it is a singlet because n plus 1, that means n is 0, then plus 1, it will be 1. So it will be only a singlet if there are no neighboring protons. So neighboring protons will split the signal. And what will be the intensity of these lines of the multiplets? It will be decided by Pascal's triangle. As per Pascal's triangle, if the number of neighbors is 0, 1, 2, 3, 4, 5, and 6, we can see their relative intensities as 1, 1s to 1, 1s to 2s to 1, 1s to 3s to 1, 3s to 1, 1s to 4s to 6s to 4s to 1, and so on, because the pattern of the multiplet will be like this. If it is if no neighbors are there, it will be in the form of singlet only because it is created by 0 plus 1 and plus 1 rule. So it will be 0 plus 1 means 1, that is singlet. Then 1 plus 1, if one neighborhood proton is there, it will be 2 in the form of doublet. Its intensity will be 1s to 1. If the neighborhood protons are 2, then 2 plus 1 means 3. The signal will be in the form of a triplet. Then the intensity will be 1s to 2s to 1, and so on. We can do. Yes. So how we can see this this splitting on a chart paper? It will be when it is a singlet, it is in this form. When doublet, then 1s to 1 intensity this form. When triplet, the signal will be splitted in the form of 1s to 2s to 1. Means the peak area will be like this. So triplet, the quartet will be in this form, 1s to 3s to 3s to 1. And later we can see others here. So now we are going to understand the splitting in different molecules by knowing these examples. So suppose this is the molecule of propane. We can see here, this is one set and this is also one set, means these six protons are of the same type. However, they are seen in two sets, but actually they are one set. So these three hydrogens plus these three hydrogens are in the same chemical and magnetic environment. Therefore, they will give only one signal, and these two protons are from different sets. So B type of proton. The total number of signals will be 2. Now the splitting pattern will be as per the n+1 rule. Here n, the neighboring proton for A. A protons are 6 and neighboring proton for them are n+1. Neighboring protons for them are 2 because methylene protons are the neighbors for these 6 protons. Neighboring protons are 2. So 2 plus 1, that means a triplet. Here, yes, and for 6 protons, there are 2 protons as neighbors, and for 2 protons of methylene, there are 6 protons of neighborhood. So there will be a septet. So here n equals to 6 means 7, or that is septet. Yeah. So A splits into 3, that is triplet, and B splits into 7, that is septet. And now neighboring protons that are equivalent to the protons whose signal is being generated will not split the signal. Yes, like this, we have done this example already, that CH2 and CH2, they are seen different, but they are in the same chemical environment. So they are in the same chemical environment. Therefore, they are the equivalent protons. They might be seen in two groups, or two sets, but they are equivalent because both of them are attached with the same halogen atom, chloride. So A type of signals will be there. The number of signal will be 1 only, and there will be no splitting. So no, in the neighborhood, no non-equivalent proton is there. Therefore, we will have a singlet only. So splitting is usually not observed if the protons are separated by more than 3 sigma bonds. For example, here the protons, there will be 3 signals, A, B, and C. 3 signals because of 3 different sets of protons. So 3 protons of A are not coupled. These 3 protons are not coupled by the B protons or the C protons because they have become separated by 3 bonds. So 0 plus 1 will be singlet for these 3 protons. Now 2 protons of B, they will split. These two protons of B will be splitted due to the presence of these 3 protons. So these 2 protons will split the signal of these 3 protons, and these 3 protons will split the signal of these 2 protons. So for 2 protons of B, it will be a quartet, and 3 protons of C, there will be a triplet. Now, what is the peak area and how we can get the information by the number of protons, or we can count the protons of any type of. So it is an example of paraxylene. In the paraxylene, this is the molecule of paraxylene. It is an aromatic ring. And here we are having CH3. Here CH3 is there. So, and here also four hydrogens are present, but all the hydrogens are in the same environment, and these two sets means one type of protons. So both of them are equivalent protons. All the 6 hydrogens are equivalent, and these 4 hydrogens are equivalent. So there are total 6 protons of one type and 4 protons of other type. Here we can see that there are 2 signals. There is a signal of HB. HB means these protons are HB. These are the HB protons, and these are HA protons. These HA protons are having lesser delta value, or they have the value of chemical shift lower. These are having the chemical shift lower. They are more shielded. Yes, they are more shielded than these Hb protons. Moreover, we can see here by the height or the peak area, we can determine the number of protons of any type, like Ha peak is more than Hb, and the ratio of their height is 1:1.5. This is why, because there are 6 protons of one type and 4 protons of other type. So 1H NMR spectroscopy, through 1H NMR spectroscopy, the area under a signal is proportional to the number of hydrogens to which the peak corresponds. So different applications are there. However, many of them we have discussed already. Identification of structural isomers, mixture analysis, qualitative and quantitative analysis, compound identification and confirmations, chemical manufacturing and food industry, biological and biochemical research, pharmaceutical development and production, agrochemical development and production. And all of them we are doing by the structure elucidation through NMR spectroscopy. So these are some of the references. You can go through them for more details. And thank you.